So today we're going to do a review of binary. Oops. All right, so binary is base 2, and therefore it has only two symbols, 0 and 1. And just like decimal, when counting, when you run out of symbols, you roll over to 0 again, to 0, and add 1 to the next column. So you would be counting 0, 1, 1, 0, 1, 1, 1, 0, 0, etc. 0, 1, roll over to 0, add 1 to the next column, add 1, add 1, roll over to the next column, add 1 and 1 is 0, carry 1 over into the third column. So that's how that's how counting can be done. Because of that, you can count on your fingers up to 1023, 1023. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, etc. Finger up is a 1, finger down is a 0. You can count on your fingers up to over 1,000. So not just a 10 anymore. Now the places, very important to remember these. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 4. Just like with base 10, only with the base of 2. And the values of each column, each digit, are multiplied by the power of 2 for that position. Those powers of 2 are 1, 2, 4, 8, 16, 32, etc. Keep on going. So when converting from base 2 to base 10, say your number is 1, 0, 1, 1, 0, 1, you would multiply 1 by 32, 0 by 16 is 0, 1 times 8 is 8, 1 times 4 is 4, 0 times 2 is 0, and 1. And then add them up together. And you would get 45. Base 10. This would be base 2. Now, when you're writing out your numbers, put the subscript in there to indicate which is which. Is this 101,101? Or is it 101101 in base 2? To avoid confusion, when you write it out, you put the subscript of 2 of the base. When you write the decimal equivalent, write the 10 in the subscript to indicate that it is base 10. All right. There are other ways to indicate that it is base 2 as well. You can, for example, this number, do 0, B, 1, 0, 1, 1, 0, 1. The 0B indicates that it is binary. When you're writing in assembly code later on in the semester, this is the notation that the computer uses to distinguish that this is, to determine that this is a binary number, not a decimal number. So 0B followed by the number, or the number with the subscript of 2. For decimal, just the number in the computer, or with a subscript of 10 when you're writing it out. Now math, let me go ahead and do conversion from, let's see here, 53 base 10 to binary. Now it's good to remember your powers of 2. Write them out to the side if necessary. Yeah, it's more than enough, up to 256. To convert from decimal to binary, the method that I choose to use myself is take the number and subtract the highest power of 2 that's less than that. So in this case, 53 is between 32 and 64, so you subtract 32. And you get 21. That indicates that there's a 32 in there, so you put a 1 in the 32's position. Now, can you subtract 16 from 21? Yeah. So subtract 16, and that gives you 5. That gives you 1 in the 16's position. Can you subtract 8 from 5? No. So you put a 0 in the 8's position. You can subtract a 4. So put a 1 in the 4's position. And then can't subtract 2 from 1. But you can, so you get a 0 in the 2's position. And finally a 1 at the end. So that's your equivalent in binary from decimal. The other way of doing it is to that I've seen is common in programming to do is take your 53 divided by 2, and what your remainder is gives you a digit. So 53 divided by 2 is 26 with a remainder of 1. So that gives you a 1. Divide 26 by 2. And the remainder is 0, 13. So it gives you a 0. 13, 2 divided by into 13. It goes 6 times with a remainder of 1. So it gives you a 1. 2 into 6 gives you 3 with a remainder of 0. With a remainder of 0, so you get a 0. And then 2 into 3 is 1 with a remainder of 1. Gives you a 1. And the 1 left over gives you your first one. So both methods are equally effective. I personally prefer the subtraction method. This is it's easier to program this than it is to program this. So the division method is often used in programming to convert decimal to binary, to a binary string. So those are the two methods that I've seen for converting decimal to binary. All right, so math with binary. Addition works just like decimal. 1 plus 1 is 2, but you don't have a symbol for 2, so you go to 0. Carry the 1. 1 plus 1 is 0. Carry the 1. 0, carry the 1. 3 is 1, 1, so 1, carry the 1. 1. And then 0, carry the 1, 1. So works just the same as decimal, just with fewer symbols. Okay. Subtraction is the same as decimal in that you add a negative number. Now, how do you represent negative numbers in binary? Well, that you use 2's complement. So if you have a number, say that this number that you want to make it negative, you first determine how many bits you're going to be using to represent the number. In this case, we have 6-bit numbers. You generally want to use groups of 8 bits when doing math and representing binary numbers in the computer. 8 bits makes a byte. So rather than adding these two numbers, let's subtract them. First, make this number a negative number using 2's complement. So take it over here. 1 0 1 0 1 1. That's 6 bits. Let's make it 8 bits with leading zeros. The leading zero here indicates that this is a positive number. To make it a negative number, you invert all the bits and add 1. So it'll be invert the bits and then add 1. So 1 1 0 1 0 1 0 1. Okay? See how I did that? Invert the bits, zeros become ones, ones become zeros. And then you add 1 to it, and you get the negative number, the negative of this number in 2's complement. Okay? I should have gone over this a little bit more detail in digital logic, but you know how that actually works on the number line and all that sort of stuff. But I'll just leave it at this process at this for this review. So you have this negative number in 2's complement. Now you want to add this number to it. Addition is commutative, so you can add in any order. So it's 1 0 1 1 0 1, right? And then you add the leading zeros. One and 1 is 2, so that's 0. Carry the 1. 1. 1 and 1 is 2. 0. Carry the 1. 0. Carry the 1. 0. Carry the 1. 0. Carry the 1. 0. Carry the 1 again. 0. Carry the 1. And your most significant bit in subtraction gets ignored. This is just garbage. So the difference between this number and this number is only 1 0. So let's check this in decimal to make sure that we're right on this. So as I recall this from the previous screen, that this was 45. And this is 32, 40, 43, 43. That's minus is 2, and 1 0 is 2. So it works out. Did I go too fast? It's supposed to be all covered in digital logic, but I do a refresher in this class because it's just good to remember this sort of thing. But yeah. Yeah, when you're doing subtraction, yeah. You make it a negative number and then just add it to the first number. It's just like in decimal. You can add 45 to negative 43 and you get 2. So subtraction is just addition with a negative number. And in hardware, that's how it's handled. You invert, add 1, and then run it through the same adders that you would for addition. We'll get into that later on in, when we discuss arithmetic logic units. Generally, you do it in groups of 8. But if you're dealing with particularly large numbers, you can do groups of 16, 32, 24, multiples of 8.
That was one of the problems that I personally had.
Okay.
Zeros and whatnot.
Just add enough zeros to make it make the number of digits a multiple of 8.
First multiple of 8.
Yeah. So in this case, we had 6 digits. We added 2 to make it 8. So that's addition, and subtraction. Just you remember the invert and add 1 for the 2's complement. So when you see a number that has leading zeros, you know it is a positive number, because this indicates I should say this indicates a negative number. The leading 0 leading 1 indicates a negative number, and the leading 0 indicates a positive number. So if you are converting a negative number, say negative 28 in base 10 to binary, you would first convert 28 to binary, and then take the 2's complement to make it negative. So you have here, you could take 1/16, which would leave you 12. You take an 8, that'll leave you with 4, and then a 4, and then no 2's and no 1's. So that's your 28 in equals 28 base 10, and then to make it the negative, add, 3 leading zeros, invert, and then add 1. So 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. And that is your negative 28 in base 10. So now with multiplication, It works basically the same as decimal as well. So you have a number times another number. Since you're only dealing with ones and zeros, the math, the multiplication is a lot easier. So you have 1 times 1011 is going to be 1011. The shift and add method, you would then go to the second digit of the second factor. 0 times that is zeros. Shifted over one position because it is the second digit. And then 1 times 1011 again is 1011. And those are your partial products. And then just addition again. 1, 1, 1, 0, 1, 1. Now let's see if this is right in decimal. So 1011 is 8 plus 3, or plus 2 plus 1 is 11. 8 plus 0 plus 1 is 9, right? No, that's not 9, that's 7. It's 4 plus, no, 5. 5. I'm not remembering my positions. 4 plus 1 is 5. So the 11 times 5 is 55. Okay? So what's this? This is 32 plus 16 plus 4 plus 2 plus 1. And that's 20, 52, 55. So it worked out. So when we get into hardware multipliers, we will discuss how you can do this in circuitry. So the computer can, rather than doing a loop 5 times adding 11, which would work, it could just do this all in circuitry. Because I don't know if anybody's ever expressed this or not to you. Anything that can be done in software can be done in hardware. And if it's done in hardware, it's done faster. So rather than having a loop in software adding these together, you can have a hardware multiplier multiplying it out much faster. So that's how multiplication works in binary. So like I said before, division and using the shift and subtract method is beyond this course. I believe it's done in 412 in computer architecture. I think it's 412, but it'd be your next class in this cycle. But any questions? You want more examples? Yes. Sure. All right. Any other questions? Is this jogging your memory from digital logic and or intro to ECE? But I know in my intro to ECE class, I cover binary and basic operations. I try to do it in more detail in digital logic, but I didn't have all of you for digital logics. You, I believe, Manzul taught some. Yeah. He taught the other section last semester. Yeah. Any other questions, or we can wrap it up for the day? All right. Well, guess that'll be it. We'll cover hexadecimal on Friday, and we'll go from there. Have a good day.